CTO at VMware. Those that were here last year might remember that I gave a talk about uses of virtualization for HPC, which is my sole focus at VMware. In that talk, I gave you an understanding of the use cases, but I also talked about our need for RDMA support in the platform. At that point, it was a wish. I continued over that last year to attempt to influence people internally within VMware around some of the issues that are important for HPC, and probably my biggest success is embodied in the fact that Bhavesh is here. So Bhavesh is a longtime VMware employee. He's an expert in virtual networking, and essentially has spent the last year looking at RDMA issues. And the bulk of this talk is going to be with Bhavesh giving us a dump, essentially, of what he's been looking at over the last year or so. Before we get to that, I do want to give you a little bit of information from a research note that we'll be publishing imminently. I was hoping it would be done by the workshop, but we didn't quite make it. We did some testing looking at point-to-point, so back-to-back TDR, vSphere systems using RC and pass-through mode on our platform to get some sense of what the latencies were, what sort of latencies were achievable on the virtual platform. So you probably can't see these, and that's okay, but what you see on the left-hand side is send latencies. Ours is the higher graph. On send, we have as low as 1.75 microseconds, which is about a 0.4 microsecond overhead. On the right-hand side, we have RDMA read, where we're at about 3 microseconds, which is an overhead of about 0.7 microseconds from native. And then looking at, and those are both with polling completions. Now this is using interrupt completions, and I would mostly pay attention to the two bottom curves. And essentially what we're showing is about a 7.6 microsecond latency on our platform with an overhead of about 3. There's good news and bad news here. The numbers from an absolute sense for many of our customers are actually very, very good. From an HPC perspective, there's still a pretty large percentage overhead. We take these as a starting point. We're really, I'd say one of the other general successes that I've had is that we have a lot of effort now going on internally within the company, looking at latency and across the board, looking at ways of driving latency down. So I expect that these numbers will get better over time. And obviously, this is, as I said at the beginning, we need to be looking at things like jitter, and we need to start running some MPI applications at scale to get a much better sense of what we can actually do on the platform at the app level. So with that, I'm going to turn it over to Bhavesh to really talk in a lot more detail about what we've been looking at with respect to RDMA at the hypervisor level and also RDMA at the VM and guest level. And in the interest of time, we very much want to answer your questions, but we also want to get through the material. So if you could hold questions to the end, that would be great. Thanks.
Thank you, Josh. Okay, so since Josh just presented our initial performance results of InfiniBand to the guest level of the pass-through, I thought we would first cover what we've been doing, looking at virtual machine and guest level RDMA support, and then the latter half of the talk we'll talk about hypervisor level RDMA support. So here are some of the options we considered on how you could offer RDMA services to guest OSs or virtual machines. I draw the distinction between virtual machines and guest OSs because when you talk about offering RDMA to a virtual machine, it's a device, a real device or a Paravirtual device that you expose to the guest OS, and then the drivers don't know any different. They think they're talking to a physical device. Versus guest level RDMA, where you can have an emulation of RDMA services within the guest OS, something like SoftROCE. So we'll get into those distinctions. So let's jump into them. Option A is to offer full function VM DirectPath, which is also known as pass-through, where you punch a hole through the hypervisor and directly expose your physical HCA, RDMA capable HCA, whether it's InfiniBand or IWAP or Rocky, straight to the guest. This requires IOMMU support on your platform. So DMAs are happening directly from the HCA to guest memory, with the hypervisor not knowing anything about those. So this, as you can imagine, since the hypervisor is not in the path, the IO path, it has no visibility to what the driver in the guest is doing to the physical HCA. So it's incompatible with a lot of value-added features that virtualization brings to the table. Some of them include memory overcommits. So this requires that all of the guest virtual machines' memory is pinned in a hypervisor. It's not swappable. So one of the features, VMware and other hypervisor vendors provide is memory overcommit, that you can have more virtual RAM in your system than there is physical RAM. So having your memory pin, your entire virtual machine's memory pin in stacked memory is not available for sharing on a platform. Fault tolerance is another feature where we have lockstep active standby replication. Again, that requires that every I/O be intercepted and we know what's going on from the virtual machine, so we can replicate that state of the virtual machine, the changes in the state of the virtual machine on the second one. Since we're not in the I/O path there, the hypervisor is not in the I/O path, we can't offer that. Snapshots is a critical and very important feature of virtual machines, the containers, and you can take a snapshot, archive it away, restore the snapshots in case you messed up your virtual machine. Again, because we are not in the path, we cannot offer snapshots. Also suspend to zero. I'll get into vMotion in the latter half of the talk. It's something we have been able to take advantage of RDMA from. But again, DirectPath is incompatible with vMotion, so if you choose to use DirectPath in the virtual machine, you cannot vMotion in the virtual machine. Option B is an extension of option A, but in option A, you could not share. The HCA cannot be used by anybody but that virtual machine to which the HCA is exposed. Neither the hypervisor can use it, nor can other virtual machines use it. With SRIOV, single root I/O virtualization, which is the PCI 6 standard, you can now partition your HCA, physical HCA, into virtual functions, and you still have the physical function, which is where all the control operations are done. But the virtual functions can now be direct assigned to different virtual machines. And you have a driver in your hypervisor which is controlling the physical function and still coordinating the partitioning of your HCA and things like that. Here, when the VF is direct assigned to the virtual machine, you still have an I/O menu and all DMAs are going straight to the guest. Again, so the hypervisor is being bypassed for this. So again, it's incompatible with a lot of our value-add features that virtualization offers. Option C is one of the guest-level RDMA approaches. This is by using the SoftROCE driver from System Fabric Works, which is, it binds to regular Ethernet devices in the guest. So you can imagine passing through or direct assigning a 10 gigabit physical NIC to a guest, or whether it's a full function pass-through or SRIOV pass-through with a VF, doesn't matter. And then you can have the SoftROCE RXC driver bind to this Ethernet device in the guest, and you can have the OFED stack on the top and those applications talking to it. Now this enables you, if this worked, this would have enabled you to talk on an Ethernet fabric between either virtual machines on different hosts or a virtual machine on a vSphere host and a physical machine. Unfortunately, this needs some debugging. Things didn't quite work. When we tried testing this, we got a completion error. And talk to the Mellanox folks later to figure out what it means. Option D is, instead of direct assigning your HCA, now you use a Paravirtual Ethernet-based virtual NIC in the guest. So VMXNet 3 is the Paravirtual, is our highest performing virtual NIC that VMware has to offer. It emulates 10 gigabit for in software emulation. Gigabits don't matter. It's your memory bandwidth that you're constrained by. But if we pretend like it's a 10 gigabit NIC, it has all kinds of offloads that you expect from a 10 gig NIC. TSO, LRO, RSS, MSIX vectors, all those things. So you can use the SoftROCE driver again, bind it, bridge to the VMXNet 3 virtual NIC. The NIC is itself, the I/O path is now emulated in the hypervisor. And by doing this, you regain all the properties that you lost by doing DirectPath, because every I/O is going to our emulation layer, and we know what state changes are happening to the device. And now this still enables your virtual machine to talk to virtual machines on other physical hosts or to physical machines which are on Ethernet. They're RoCE connected.
What's the latency in that?
So I'm going to get into the performance aspects in a couple of slides. So this is option D is about essentially talking between hosts, a virtual machine on one host to a virtual machine on the second host, or a physical machine. And so as I said, it doesn't rely on DirectPath, so you get back all your features from VMotion as VM. Okay, option E is essentially the same as option D, except this is VM to VM communication on the same host. So you go through a virtual switch on the ESX host, and it's still binding to the VMXnet3 NIC, which is connected to our virtual switch in the hypervisor. And this requires SoftROCE in both your virtual machines bound to VMXnet3. Again, we'll look at the latency in a couple of slides. And option F is what I consider the holy grail that we're trying to achieve, which is a new paravirtualized RDMA device. This is exposed to the guest as an RDMA device, and you have an RDMA vRDMA HCA driver that we provide, and the OFED stack on top. And the emulation of this Paravirtual device is done in the hypervisor. It essentially translates verbs that you get down from the OFED stack to a hypercall interface down to the emulation. And then you translate those verbs down to a minimal OFED. ESXi, by the way, that we have multiple ways of referring to our hypervisor. It used to be called ESX, and then we invented the term vSphere in version 4.0. So I use these terms interchangeably. The core of the hypervisor is called VM kernel, that's the kernel. And ESXi is the kernel plus other components that go into the hypervisor. And vSphere is a marketing name for it. So you need a minimal OFED stack in the ESXi hypervisor, and the device emulation would translate the verbs down to verbs in the OFED stack, the ESXi layer. And then you have your physical HCA device. Now this can again be any of the HCA technologies. It could be InfiniBand, iWarp, or RoCE. So the DMAs, one thing to note here is DMAs are still zero copy to and from guest memory. So essentially when the application in the guest OS registers memory regions, the guest physical memory that it specifies in those memory regions are the physical regions that we program down to the physical HCA. So that when RDMA is complete, the memory is being DMA'd to guest memory. Right? There's no copy involved in the hypervisor. The only intercept where the hypervisor is involved is proxying of completions and interrupts. Interrupts still go to the hypervisor.
So if a VM pre-pins all its memory through verbs, then all the memory for that VM is pinned anyway, right?
No, so that's a good question, whether a VM would need to pre-pin all the memory, and it wouldn't in this case because it's our driver which is being told, a Paravirtual HCA driver knows what memory regions are being described in a verbs command. So it only needs to pin those memory regions, that region of guest physical memory.
If the guy decides he wants to re-register all the RAM.
That's right, yeah. If you still have an application or a guest OS which says, I want my entire guest memory addressable to RDMA, then you have pinned the memory. Yes. We hope that most applications or most guest OSs will do that. And even if they did, by the way, you still get the features that you had lost. You can still VMotion, snapshot, and suspend reserve. The only thing that you lose is memory over commit, right? You cannot share that memory. Okay, here's the performance question. What kind of half-round trip latencies we can see. The first one is just native InfiniBand, two back-to-back connected machines with ConnectX 3 actually. Native InfiniBand, which is about 1.2 microseconds. This is the RDMA write operation, and this is 2 byte messages. So we're trying to get the lowest number we could. So native is 1.2 microseconds. Native to a pass-through device in a virtual machine is 1.53 microseconds. This is sort of consistent with the numbers Josh presented. They might be slightly off because it's a different machine and different NCA, but they're in the same ballpark. Now, when you go to SoftROCE, somebody asked what the latency effect is. You can see the dramatic increase in latency there. with SoftROCE. Now, if you do SoftROCE over a 10 gigabit physical NIC as an uplink, it's about 15 microseconds round trip. These numbers are still pretty good compared to virtual networking numbers, but they are nowhere near what we would expect in HPC or even for low latency enterprise applications. If you do virtual VM to VM communication over the vSwitch, they're even higher, about 18 microseconds. And the last bar is what we expect. So we're prototyping the virtual RDMA device right now in the office of the CTO, but what we expect based on back of the envelope calculations is about 5 microseconds. So it's still higher than what you can get in pass-through or native, but we think it's good enough for enterprise-based applications. And this calculation, by the way, these numbers are of course with polling mode. So there are optimizations we can do in paravirtualization of this device, including using polling instead of interrupts, because interrupts are expensive. Proxying interrupts can also be expensive. There's tricks we can do with, one of the things, enabling technologies for virtualization is VT or AMD RVI, which is, have an ability to tell the processor to take an exit when some privilege operations are done by the virtual machine. Those exits are expensive. In the newer generation of Intel processors, they're still about 700 to 800 cycles for an exit. So every I/O operation, privileged I/O operation, costs you 700 or 800 cycles every time that happens. This includes exits for various reasons, whether it's for I/O, or for proxying an interrupt to the guest, or for page faults, or for any of those operations. So there are things we can do which avoid the need for exits by polling both in the guest level and at the hypervisor level for requests being posted by the guest or completions being posted by the hypervisor to achieve low latencies. No, so the question is whether I have SROV numbers. I don't for this experiment, but we expect SROV and full function pass-through to be exactly the same. There shouldn't be any difference because the I/O path is the same. So here's a summary of where we stand with virtual machine and guest level RDMA. Option A is already being used by some of our customers, full function pass-through. Option B, which is SROV, will be offered in an upcoming release of our product. Option C, D, and E are SoftROCE in the guest, which can already be done in vSphere 5.0 shipping version of the product, but it costs you in latency. On the flip side, it preserves all your value-add features of virtualization. Option F is what we would really like to get to, and we are currently prototyping that in the office of the CTO. Yeah, question?
So for the option F, what kind of dependencies, if any, you might have on the underlying HCA provider?
We don't really have any special dependencies on the underlying HCA provider. We need an OFED stack. We need verb support at the kernel level. Right.
So most of the latency in proxy is actually caused by interrupt moderation and the NAC algorithm. And that parameter varies widely between different physical NICs, but I don't know, in your case, the NIC would be a virtual Ethernet device that you provide. And somebody, whoever set that up, set up a tuning parameter which tells NAPI how long to disable interrupt for, and that turns out to be the predominant cause of latency there. So you could probably make that shorter by changing the interrupt moderation characteristics of the driver.
Yeah, that's a good point. So one thing I should have mentioned in the setup for like the pass-through case where we used a 10 gigabit NIC is we did turn off interrupt moderation on the 10 gigabit device. Using
the external device.
To the physical device, yes. And the same thing for the virtual device, for the VMX Net3 device. We have an option, a config option to turn off interrupt moderation in the hypervisor. So every packet that comes in immediately generates an interrupt. Now, NAPI is another point, is how long does NAPI run? We have been looking at completely non-NAPI, going back to non-NAPI. NAPI is great for throughput, gives you the high throughput at lower CPU utilization because you don't generate as many interrupts. It's pretty bad for latency because a packet arrives and it can be queued with other packets and batched, delivered to the virtual machine. So we're looking at a non-NAPI version of the VMXNet3 driver as well. And we would like to see the same thing for other Ethernet things. But everybody has moved away from non-NAPI to pure NAPI now. Yeah.
So after you get the option F, are you then going to try to tackle
That includes option F. Prototyping includes getting VMotion working with option F. Now, if you go back to option F, you look at what's involved in implementing it. It's a device emulation in the hypervisor. Anytime you introduce a new device in the hypervisor, it's almost a mandate within VMware that it's got to be VMotion compatible. First, it's got to be snapshot compatible. By being snapshot compatible, you get VMotion for free.
But I mean, for example, when the thing is in motion, we don't have a lot of ICP.
That's right.
The RDMA packet, where is it going from the other side? So it's just, you have to reestablish the change.
That's right.
Unless you're doing a lot of other factoring.
No, you have to you're right on all those fronts. On the destination host, you have to reestablish new connections as a proxy for the virtual machine. Yes. You're aware of those. Okay. Okay, so now let's switch gears to talking about how RDMA can be useful at the hypervisor level. Here's the architectural picture of our virtualization stack. On the left-hand side are 3 virtual machines with paravirtual NICs, virtual or paravirtual NICs. I draw the distinction between virtual and paravirtual because virtual is an emulation of existing physical NICs. We emulate Intel E1000 and E1000E NICs. And the first NIC we emulated was VLANs, AMD's LAN spur. And paravirtual are things like VMXNet3. And those are connected to our virtual switch ports. In this picture, you can notice there's a TCP/IP stack on the right side. That's a VM kernel or hypervisor level TCP/IP stack. It's derived from FreeBSD. And it has the hypervisor services like iSCSI on the host, NFS, fault tolerance, and VMotion on the host use the TCP/IP stack. But traffic which goes in and out of virtual machines does not go through the TCP/IP stack. So one point to remember. So what we're looking at is VMotion currently relies, all these services currently rely on a TCP/IP stack. If we could have an alternative transport of using verbs instead of TCP/IP, we could get some of the benefits of RDMA. So the ladder graph is talking about that. Now the prototype was done with Rocky here, so that it's, we can still use FT and iSCSI and NFS and even VMotion with the existing TCP/IP stack over Ethernet. And then we can flip back and forth between Ethernet and verbs as either performs. Go a little bit into what VMotion is. It's basically live migration of running virtual machines. It's a key enabling technology for other VMware technologies like distributed resource scheduling and distributed power management. VMotion's data transfer mechanism currently relies on the TCP/IP stack. At the API level, it relies on BSD MBUF level APIs. It's not sockets per se, it's BSD MBUFs because we use zero copy sends and receives, and we can tag on buffers to MBUFs and so on. So why would you look at RDMA? For the obvious reasons. This is a classic use case for RDMA where you can benefit from zero copy sends and receives, thereby reducing CPU utilization in the hypervisor. RDMA offers lower latency and it eliminates the entire TCP/IP stack and protocol overhead.
Bhavesh?
Yeah.
So if the RDMA is actually used for VMotion, what would be the end customer benefits? If all these things are achievable, are they able to put more VMs on a particular host?
Yeah, that's a good question. So there's several benefits of RDMA if VMotion was to go over RDMA. There's reduced CPU utilization, both at the host, that source and the destination host during the RDMA. There's faster VMotion times. If you have large VMs, you can migrate the VMs faster. For scenarios like evacuation, where you have to evacuate tens of virtual machines on a given host, you can evacuate them faster. And you can make use of the CPU cycles you have for running more virtual machines on the same host as well. Consolidation, classic value proposition. Okay, so here's some basics of how VMotion works under the covers. It has 4 primary stages it goes through. There's a pre-copy phase where the virtual machine on the source is still running, but we are aggressively copying memory as it is being modified from the virtual machine on the source to the destination host. And the source doesn't know anything is different. The virtual machine on the source is still running. Followed by a quiesce phase where the source virtual machine is quiesced. It's not allowed to do any more operations, the vCPUs. The virtual CPUs are stunned. So there's no more device state changes happening. There's no more memory being modified after the quiesce phase. Followed by page in. So once this is happening on the destination host, any pages which were remaining on the source host between the pre-copy ending and just before resuming the virtual machine on the destination need to be paged in on the destination. Followed finally by unstun or resuming the virtual machine on the destination host and letting the vCPUs go. So the downtime, you can imagine the VMotion downtime is really the time between quiescing and unstunning, the time that the vCPUs on the source host are stopped and they're resumed on the destination host. And we want to minimize that as well. And of course, the majority of the transfer is transferring of pages, 4K pages, which is done during the pre-copy phase and the page-in phase. And the majority of that page transfer is actually done in the pre-copy phase. We try to converge the pre-copy phase in such a way that during the page-in phase, there's only about half a second worth of outstanding pages. So this is to minimize the downtime, guarantee that the downtime is no more than half a second. And those are tunables, internal tunables. Now, in the TCP IP-based approach, there are multiple VM kernel. Remember, VM kernel is the core of our hypervisor. So there's multiple helper tasks which are pushing data and receiving data as fast as possible. By default, it uses 2 helper tasks on the source and 2 helper tasks on the destination. In 5.0, which is our currently version of the shipping version of the product, we also introduced a new technology called STPS, done during page send. The idea here is if your source virtual machine is dirtying or modifying memory at a faster rate than you can transmit your bandwidth and sustain, then you have to stun or slow down the vCPU on the source host so that it doesn't dirty as much memory. So that eventually we will converge and only have about half a second worth of pages outstanding at the end of this. So yeah, that facilitates pre-copy conversions. Here's the state transitions, and actually this is more about the operations for data transfer itself, or page transfer. So on the left-hand side is the source, right is the destination. In the TCP IP approach, first thing you do when you're sending a bunch of pages is you send what are PPNs. They are physical page numbers. In VMware, we draw the distinction between PPNs, or physical page numbers, and MPNs, which are machine page numbers. Machine is what you think of as physical and non-virtualized. So first step is sending the physical page numbers, what the guest OS sees, what the virtual machine sees. The second step is pinning the physical pages that you're about to transfer to machine pages on both the host and the source and destination. The third step is you map these physical pages to the MBUFs, the MBUFs that we use in the TCP IP stack. The fourth is actually doing the send over TCP IP through a BSD derived stack to the destination. The fifth is on the destination, these buffers were received, the packets were received in buffers allocated on the heap in the destination host. They have to be copied from the heap memory into the destination buffers, which correspond to virtual machine memory. So there's a 1 copy involved on the destination host here. In the RDMA case, the first few steps are the same. You send the physical page numbers across, you pin the PPNs to MPNs. Now in the third step, you map the physical pages to memory regions directly, RDMA memory regions, on the source and on the destination. Now the destination has enough information to be able to do that because you send the physical page numbers across in step 1. The fourth step is sending the memory region key and IO virtual address to the destination. And In the fifth step, we let the destination issue an RDMA read. This was, again, a design choice because during the vMotion, the source is still running virtual machines. So we want to offload the source from as much of this RDMA operation as possible. We let the destination do the RDMA read instead of the source doing an RDMA write in this case. We'll describe the performance results we got with the test setup we had. Nothing spectacular, just off-the-shelf hardware. 2 ConnectX-2 Mellanox 40 gig Rocky capable NICs. The benchmark we use for virtual machines, so it's a 60 gigabyte host, and we created 56 gigabyte virtual machines with 4 vCPUs. It has 2 quad-core processors on the host, so with hyperthreading enablers, so we had 16 threads of execution on physical hosts, and we created 4 vCPU virtual machines. Just to have 12 CPUs to spare, if you will. So again, 56 gigabytes of virtual memory, so you still have 4 gigabytes left in your physical machine. There's a runtime config switch we created to flip between TCP/IP and RDMA transport. And as I mentioned before, TCP/IP by default uses 2 helper streams, 2 helper tasks to push, to send and receive data. For the prototype, just for simplicity, we did this over 1 helper thread. So this is of course going to penalize RDMA versus TCP/IP. Let's show you the results, which still gave better results. And we disabled SDPS for the measurements because SDPS, as you can imagine, can introduce variance in performance results. It's slowing down the vCPUs on the source depending on the workload behavior at any given point in time. So if the workload we chose was SpecJBB, by the way, it's a Java workload which dirties a lot of memory. That's why we chose this benchmark. It's a benchmark we like to use for measuring vMotion and a lot of other features because it dirties memory at a high rate. So depending on where in its phase of testing the benchmark it is, it may be dirtying more or less memory, and that leads to different usage patterns of the bandwidth. So we disabled SDPS just to get consistent results of TCP/IP versus RDMA. So getting into the results, the total vMotion time went down by 36% from 70 seconds to 45 seconds. The Precopy bandwidth in pages per second went up by 30%. This is 10%. So another thing to keep in mind is PCIe Gen 2, ConnectX-2. So the theoretical limit we're looking at is about 26 gigabits per second. Now, the 10.84 gigabits per second, some might wonder why is it 10 and not 26 or closer to the limit. It's a reflection of the workload, really. How much memory you're dirtying at any given time. So as I mentioned, SpecJBB dirties a lot of memory, but it's still not that extreme. There's periods of time, milliseconds or microseconds where it does not dirty memory or it's halted, the virtual machine is idle at that time. So if you had a workload where it was just dirtying a lot of memory and we're constantly transferring pages, we expect to see higher bandwidth usage. But in spite of that, we saw higher bandwidth with RDMA, higher throughput. The most spectacular savings were on CPU utilization. I need to explain this graph a little. So this is a line plot of the times you see are in seconds. So every 5 seconds, we're measuring the CPU utilization on the host. This is on the destination side, and this takes out the CPU utilization of the virtual machines themselves. So this is strictly measuring how much CPU is being used for the vMotion. So it's only about half a core being used anyway for TCP/IP. And the other thing to keep in mind is this is with 2 helper tasks for TCP/IP versus 1 helper task for RDMA. Now, had we had 2 helper tasks for RDMA, we would expect the line to be shorter because that's the total vMotion time. But it to be taller, the graph to be taller because it would use a little bit more CPU. But when I mean it's 92% lower, it's a summation of CPU utilization across the duration of the vMotion, which is 92% less in the RDMA case. And we expect that to hold even if we had 2 helper tasks.
So, I mean, it's all the copy you took out, or is it also the TCP/IP overhead?
It's both. It's a copy and a TCP/IP protocol overhead on the destination. The source CPU utilization is still pretty dramatic, 84% less CPUs. So here are the requirements of what it would take to eventually ship RDMA capability in a hypervisor. You need pieces of the overhead stack, specifically the kernel space components, the mid-layer and provider components in the ESXi hypervisor. And in doing so, we need to work out any IP legal licensing issues with overhead components because in integrating it with a proprietary VM kernel. We need to add RDMA verb support for other services like fault tolerance, NFS, iSCSI, and there's others we can't talk about at the start. Anything at the hypervisor level which has bulk data transport would easily benefit from RDMA. We need to create some abstraction layers so that other applications, other hypervisor services can easily port from EST and buff to a workspace interface. And we're currently discussing a roadmap on when we can ship this in our upcoming product with the product teams. So I'll hand this over to Josh.
So just to wrap up, so as you've seen, we've been doing work on hypervisor level RDMA. We've also been looking at the guest and VM level RDMA performance. We think we're delivering reasonably credible performance at this point for many enterprise use cases. We still clearly have work to do for HPC use cases. In terms of going after guest level RDMA, as Bhavesh said, the sort of holy grail for us is really this, as he's calling option F, is this paravirtualized or virtualized RDMA device. And that's what Bhavesh is spending most of his time on at this point. So we think we've made some progress, and we hope to be able to report more progress